So the last time I saw you was Valentine's Day. That was a fun class. I like that. Wouldn't it be nice if we had a musical interlude like that every time? So what we're going to do today is finish up this chapter and then hopefully finish the next one. So let's look at what we're here. Let's zoom in here. And we were talking about regression estimates. And let's look at the top of the page here. I'm going to hold on until everybody gets settled. Okay, now, have you heard of something called the regression effect? Have you heard of this? Raise your hand if you have. Regression effect. All right. What the regression effect is, let's look at it and zoom in a little bit so you can see a little bit better, is basically this effect that the regression estimates tend, if the correlation is not perfect, not 1 or -1, then your regression estimate is always going to be closer to the average than the independent variable that you start off with. For example, you all just took exam 1. Now, let's say you really didn't do very well on exam 1. Let's say you got a 75. Okay? That's not great for exam 1. Now, and I wanted to make a regression estimate based on past data. Usually there's a correlation of about 0.6 between exam 1 scores and exam 2 scores. And if we knew the average and the standard deviations, what they would typically be on exam 2, we could make, and we certainly know what they were on exam 1, we can make a regression estimate, and I can predict what any one of you would get on exam 2. And that prediction is always going to be closer to the average than your original exam 1 score. It's always going to be closer to the average, which means if there's a positive correlation here too, it means that you're going to, if you had a below average score on your first exam, you'd still be below average. It's a positive correlation. Below average is grouped with below average, but you'd move closer to the average. Similarly, if you had a really high score, like 95, chances are, well, the best prediction, my best regression estimate would be closer to the average. And that's not because it's not due to some psychological effect. That's the regression fallacy. Thinking that it's due to some psychological effect, that people who bomb the first exam are going to study really, really hard and then do better on exam 2. I hope that happens, and that could add to the effect, but I'm not talking about any psychological effect. I'm just talking about the math of it. And you can see that. Why? You can see that how this regression effect happens when we look back at how we were doing these regression estimates. Watch. Let's turn back to page 94. So everybody go back to 94. And here we were doing regression estimates for a large class who took 2 exams. And watch what we do. This is the procedure we've learned so far. We start with 1 score, here in this case exam 1, and we change it to a z-score, correct? Correct? And then our predicted z-score for the next for whatever we're trying to predict. Here we're trying to predict the student who got a 90 on his exam 1. What's our best guess for what he gets on exam 2? To get from one z-score to the other, we always multiply by what? What is that? R. And do you see how an R, unless R is 1 or -1, R is always gonna, R can't be, R has to, unless, if you have a perfect correlation, then the z-scores would be the same. But anything short of that, you're going to be multiplying by a number whose absolute value is less than 1. So you're going to be, in this case, it's 0.6. So the z-score is going to get closer to 0. Do you see that? Doesn't the z-score have to get closer to 0 if you're multiplying by 0.6? And what is the z-score of 0? What's the z-score of 0? It's the average. So do you see how it's always going to bring you closer to the average? If there was no correlation at all, you would wind up right at the average. That would be your best guess. So the regression estimate is always a mixture of, if there was a perfect correlation, you'd have the same ranking, the same z-score, that, and the average, which would be, you know, it's partway between those two extremes. If R is between 0 and 1, and it always will be if there's a positive correlation, then that means that your regression estimate is going to get closer to the average. How much closer? That depends on what R is. The closer R is to 0, the closer you'll get to the average. So why don't we write this down? The same thing happens here. Here we have a negative z-score. This person did below average. We multiply by 0.6, and do you see how -0.9 is closer to the average? And if we had a negative correlation coefficient here, this would be -0.6, so the person who was above average would be likely to be below average. That would be very unusual for, you know, 2 exams within the same class. But let's say there was a negative correlation. Let's say one was a math exam, one was an exam on social skills or something. And you can easily imagine having a negative correlation there, probably, especially if you've ever been to math department parties. But the thing is that if this was negative, you would still have, this would be -0.6, it would still be closer to the average. It would just be coming from the other direction. So let's write this down. This is called regression towards the mean. The mean is the average. And all it means is that, let's make a note, that your predicted z-scores, because you're multiplying by your predicted z-scores, have to be closer to 0. Because why? You're multiplying by R, and what? R, the absolute value of R is less than or equal to 1. R is between -1 and 1. So you're multiplying by a fraction, basically, and it's bringing your z-score closer to 0. That's just regression to the mean. That doesn't mean everybody's eventually going to become average and the same. No, you could easily do better than your prediction. You could do better on it. I mean, I don't want you to think there's some rule that you're going to have to, when you take exam 2, you're going to have to get closer to the average in your exam 1 score. No, I'm just saying, you know, a lot of people are going to do better than, you know, their exam 1 score, even if they are above average, and worse even if they were below average. I'm just saying the best prediction is closer to the average because most people are closer to the average. Okay, so the same is true. It's probably even easier to see graphically when we did the percentile predictions. Now, these were predictions we could use. We made these regression estimates when we had 2 sets of normalized data. In this case, they were math SATs and verbal SATs, and they had a positive correlation. And the same exact phenomena is taking place. Look, if R was equal to 1, then the 80th percentile would match up. You'd multiply by 1, you'd get 0.85, and you'd get the 80th percentile again. If R was equal to 0, then you'd multiply by 0 here, and your best guess would be right dead in the middle at the 50th percentile. But since R is 0.6, it's somewhere in between. In other words, it's closer to 0. This z-score, these z-scores right here, again, are closer to 0. So that brings the percentile closer to the 50th percentile. And doesn't that make sense? That if somebody's way out here, pretty high up, and there's not a perfect correlation, there's some uncertainty. If there's a perfect correlation, you'd end up exactly at the 80th percentile again. There's some uncertainty, wouldn't you, doesn't it make more sense to predict that he'd be lower down where most of the people are, rather than further away where hardly anybody is? Okay, so let's just note this again. It's the same thing. Note, the predicted z-scores, whatever you're predicting, are always closer to 0. Do you know what I mean by closer to 0? Look, 0.51 is closer to 0 than 0.85. Negative 0.51 is closer to 0 than negative 0.85. For whatever you start off with, you're going to move closer to the middle with your regression estimates, are closer to 0. Okay, that's all. And which means what? Which means the predicted percentile is closer to what?
The average.
Right, and what do we call it? The percentile. What is the average percentile?
50.
Right, means the predicted percentile is closer to 50th. Thanks. So that's all we're doing there. That's what regression towards the mean means. Okay? Now, the next thing that we're going to do is look at these, a regression estimate problem where first we're going to estimate y from x, and then we're going to estimate x from y. You had one of these like this in your homework. And it turns out the regression of y on x is not the same thing as the regression of x on y, and we'll see why. First, let's do the problem though. So, estimate the average height of those sons whose mothers are 69 inches tall. And we have the 5 summary statistics here. It's a group of people with these 5 summary statistics, so we can make these regression estimates. Now, don't get fooled by this language. This is exactly the same thing. This is no different than if I asked you to, this is exactly the same question as, I could phrase it, that says same question, sorry. That says same question as. I could phrase it like this. Predict the height of a son whose mom is 69 inches. It's the same thing. Because estimating the average height of all the sons is the way that you would make, whose mothers are 5'9", is exactly the way that you would make an individual prediction for a particular son of a particular mother. Okay, so now how do we do this? Well, here it just tells you what you need to do. You start with what you know, 69 inches. You're starting with the mom's height. And it's 69 inches. And we want to end up with the son's height. I guess it's mom's plural and son's height. So we want to end up with some inches here, inches to inches. But what do we have to do first? We have to convert the inches to what? What do we have to do first? We can't go directly from inches to inches, but we're going to convert first to what? Z-scores. So let's do that. So we're going to first get a Z-score for the mom. And let's do that. So we'll subtract off the average, which is 65 inches, and divide by the standard deviation of the mother's, and then we get 4/2. So the mom is 2, and 2 standard deviations above average. Now, we have to use this piece of information. Our regression estimate is always going to be closer to the average because we're going to be multiplying by a fraction here. So we're going to multiply times 0.5, and that is going to give us the Z-score for the son. So we do that, multiply by 0.5, and then we get the Z-score for the son is 1. So basically, moms are on this side, sons are on this side, and this is what relates them. Now, we have the Z-score is 1. Now, the best way to think about this is instead of solving, I don't like when people use this formula again backwards. Solve, because you know the Z-score, I guess would be Z, and then you know and now you would be solving, and you know the average, you know the standard deviation, and you'd solve for the value with these statistics here, the ones for the son. It's so much easier to just use intuition instead of doing that. What is 1 standard deviation, what does 1 mean as a Z-score? Does it mean 1 inch? Does it mean above average? Yes or no? Yes. Means above average. So just start at the average. We want inches. This is not inches. This is not inches. This is at standard units. We want inches. Just start at the average. So what is the average for sons? Look up here. What is the average for sons? 69 inches. Okay, now, if he had a Z-score of 0, he'd be right there. But he has a Z-score of 1, so he's above average. So add 1. But that is not 1 inch. Do you know what that 1 means? It means 1 what? 1 standard deviation. That's what it means. A Z-score, it tells you how many standard deviations you are above or below average. So this is 1 times the standard deviation. Now, we're at sons here, so what standard deviation do you think we're going to put in here, 3 or 2? We're at son's height, son's average, son's standard deviation. So what is the son's standard deviation? 3. So this just tells you right away, you should just be able to intuitively say, if the standard deviation is 3, he's 3 inches above average. That's what it means. And so it's 72 inches, which is 6 feet. So what we're saying is that typically speaking, there's not a perfect correlation, but in this population, mothers who are 5'9" have on the average sons who are 6 feet. Questions so far? Now it says, estimate the average height of those mothers whose sons are 72 inches. So you might think, mothers who are 5'9" have sons who are 6 feet, so sons who are 6 feet should have mothers who are 5'9". But let's just do the math and see what happens. First, let's just start with sons here. Instead of, on your homework, I think you got confused because I said it all on the same chart, like this. First, let's just start. What do we know? We know that the sons are what? The son's height is what? 72 inches. And what do we want to do with that? Change it to a Z-score. And then we're going to multiply by what? 0.5. And then we're going to get the other Z-score for the moms. And then we'll get the mom's height. All right, so let's do it. So 72 inches to the Z-score is going to be what? Subtract off the average for the son, divide by the standard deviation, and sure enough, we get 1. Now, I'm always going to get something closer to the average, right? Closer to 0. I multiply by 0.5, and what do I get for the mom's z-score? Hello? 0.5. And that doesn't mean she's like a little mom, 0.5 inch. Cute little mom. It doesn't mean that. Mini mom. What does it mean? It means that she's actually above the average mom. So let's start with the average mom, which is what? 5'5". And then we're going to add 0.5, but it's not inches. It's 0.5 standard deviations for the mothers. So what do you think goes in there, 2 or 3? Be really careful. This is a mistake most people make. We're at mothers, so what should I put in here? We have 2 standard deviations. Which one goes with the mothers? 2. 2. So how tall are the mothers? 66 inches. We could have gone backwards this way like we did. We could have, on your homework, I think you might have gotten confused because I put it on the same chart. So it's just like, I don't know, how many of you know Hebrew? Because you read, in Hebrew you don't read from left to right. You read from right to left. So if you were doing this problem in a different language, the logic's exactly the same. We're just reading across this way. Is that how it is in Arabic as well? Yes. What other languages? Japanese? Okay. So, let's do it. I just want to show you it doesn't matter if you read across this way. So what would we do? We'd say 72. Do you see how you would get 1? 72 minus 69. Should I do it like this? 72 minus 69 over 3. That looks so weird. But you would get, that looks like -1. Don't do it that way. 72 minus 69 over 3, and you get 1. You get 1. He's above average. He is above average. Now, you multiply by 0.5, and you get 0.5. And we're right here, and it's the same thing, so that you start at the average, 65 inches plus 0.5 times 2, and what do we get? 66 inches. Now that you know the math of it, you probably are still thinking, why? Why? Yeah, I know the math works out, but do I really understand why it would be that way? Can I picture it in my head? You probably can't. So let me see if I can help you do that. The way that I think the best way to picture in your head, best way to picture anything before we even get into the specifics, for me at least, is to think of 2 extreme examples, the 2 opposite ends. One opposite end is when you have an absolute perfect correlation. If you have a perfect correlation, R equals 1. Let's say it looks like, and let's say you just have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Okay? And I told you X, this is X and this is Y. I said X is 5. Predict what Y is. Well, you go right up here and you see Y is 5. All right. That's your best prediction. Now if we go in the other direction, what if you start with Y? 5. And your best and X, this is the Y equals X line. So of course it's going to be the same and symmetrical either way. It doesn't matter. The regression of X on Y is going to be exactly the same as the regression of Y on X. It's Y equals X. So if whatever one prediction is, it's going to be the other. It's total symmetry. But that is not what we have anywhere in the real world with any real world data, and certainly not with mothers' heights and sons' heights. You can't perfectly predict how tall my sons are looking at me. Okay, now, that's one extreme. Let's look at our other extreme. So there it does work. Your intuition does work. The regression of Y on X is the same. But what if we go to the other extreme when R is 0? And let's think of an example where R is 0 that we're familiar with, that we've talked a lot about, and that was predicting maybe ACT scores from height. Should we do that? Good, we'll do that one, ACT and height. So you have these little people down here that maybe are 4.5 feet. And you're going to have your really tall people up here who are what, 7.5 feet? Not very many of them. Most people are going to be in between. But the point is that you don't know anything. Just because somebody's tall or short, you don't know anything about their ACT scores. It's totally random. Is that correct? I tell you that somebody is 6 feet tall, and what would be your best guess for ACT? The average ACT of this group. What else would you guess? The average ACT. Let's say the average ACT was what? I don't know, 26 or something? Let's say the average was 26. All right, and I told you the person was 6'6". 6'6". You'd still guess the average, right? Wouldn't you? Now, okay, so somebody who's 6'6", your best prediction is a 26. But now I say, what if I tell you somebody's score is 26 and you have to predict their height? Would you predict they're 6'6"? No, what would you predict? The average height, which probably is about 5'7". Because it's all, so it's some mixture of that. It's some mixture between the average and a perfect correlation for these when there's a positive correlation. Do you understand now why it sounds nice that mothers who are 5'9" have sons who are 6 feet, therefore sons who are 6 feet have mothers who are 5'9"? But we're not in this situation right up here. We're in a mixture of these two situations. And if you want to see what the exact picture would look like, it might help you. It would look like something like, I can show you what the picture would look like and what's going on here. You've got not a perfect correlation. You got a cloud with a lot of scatter. And here's moms, and here's sons. And dead center in the cloud is what? The average mom, which is 5'5", 65 inches, she's the average. And the average son, which was 5'9", 69 inches. That's the average. All right. And now, what I asked you to do was I said, we're going up 2 standard deviations up to these tall mothers, way up here, that all are in this column. There's mothers, there's, 5'9". And I'm asking you to make a regression estimate for their sons. Some of their sons are very tall. Some of their sons are below average. They range. But your best guess would be right in the center of that vertical strip. And when we did that, that's what a regression estimate does. It gives you that, and we saw that that was 72 inches, 6 feet. That's our best guess. Okay? Now I turned it around and I said, let's look at all these guys who are 72 inches. They range, they have mothers, some who are very short. Some do get as tall as 5'9", and some get up here. And now, should we pick the very shortest mothers? Should we pick the very tallest mothers? Should we go way up here and pick 5'9"? No, that doesn't make sense. Wouldn't you pick the average, the middle of that horizontal strip? Wouldn't you? Which would be right about here, towards the average. See? This is regression towards the average. And that is 66. So that's the idea of it, and you're going to see more. Later, we're going to learn another way to make these regression estimates. Instead of doing it through converting to z-scores, we are going to get the equation for this particular line, which is the regression line, and we'll see it's not the same when you're regressing, when you have x, when you're trying to predict y from x. It's not the same. You're going to have a whole different line when you switch the y and x axes. It would be a different line completely. And you'll see that later on in chapter 9. So, read the summary. Now it's time to do chapter 8. All right, bear with me. This chapter is boring. I don't know how to make it interesting. Maybe if you ask me questions, it'll be interesting. I don't know. I find it boring. Most students find it worse than boring. They find it frustrating. I'm going to try to make it just boring without being hard. I mean, if I can make it interesting, I will. But you got to help me out, because I don't know how to make it interesting. You'll have to ask me questions or something. I'll try. So why do I say it's boring? What is this about? This chapter, first of all, just check out the title. The Standard Deviation of the Prediction Errors, also known as the root mean square of the errors. There's so much language there, it probably makes your head spin, right? All this is saying is that when you make a regression estimate, unless it's perfect, unless you can make a perfect prediction in every single point and you have no error, you're going to have some error. Like if I'm going to predict one, whatever I'm predicting, like here's how you did on exam 1, let's say I'm going to predict how you're going to do on exam 2. Okay? Based on, let's say everybody took exam 1 and exam 2 except you. The entire class did. So now I have data on all your stuff. Tons of people's scores, and they're scattered everywhere. There's not a perfect prediction. They're scattered, but there is a positive correlation. So I'm not going to just guess the average for you. You tell me what you got on exam 1, and I can have a better estimate than if I know nothing about you. So they're scattered. So what happens? So let's say whatever you get on, let's say you're right here. I don't even have to, I'm just doing a general thing. I'd go straight up here. Okay, that's your prediction, whatever that number is. So I could give you an estimate. Okay, that's what you're going to do on exam. Let's pretend that was a 90. Okay, let's pretend that was, I said you're going to get a 90 on exam 2. But what you're interested in is, I could get a 90, but I want to know how far off it could be. Look at all the people who did so poorly and all the people who did so well. I want a way to describe this spread around the line. It's a very different situation if I predict a 90 and it looks like this than if I predict to you a 90, the same point, let's say it was still a 90, but it looked like that. Almost every, then I could say, you're going to get a 90, give or take 1 point. Isn't that hugely different than if I said to you, I predict you'll get a 90, give or take 10 points? It really makes a big difference to you. So that is what this chapter is about. How do you calculate that? You want to make an estimate, but you also want to give people a margin of error around it. That's what this is, the prediction errors. The size of the prediction errors, the typical size of the prediction errors. That's what this measures. Typical size of the prediction errors. What are prediction errors? You make a prediction, and if you're off the line, there's an error. I make a prediction you're going to get a 90. If you got a 92, your error is 2. If you got an 87 when I predicted you'd get a 90, your error is 3 below, -3. So I want to know what the typical size of these prediction errors are. So a distance a point is off its predicted line, off the regression line, is its prediction error. Another word is its residual. Lots and lots of language that people use for this. And the prediction error is just your like here's an actual value, and there's its predicted value. So it's just this distance. That distance is a prediction error. Okay? That's the size of the prediction error. It's the distance off the regression line. And if it's above, it's positive, and if it's below, it's negative. That's all it is. Okay? Now, what's this? I just straightened the line out so you could see, read them better. I straightened it out at 0. And here's a very interesting fact that relates back to what we talked about with deviations from the average. For any regression line, the average of the errors is always 0. Remember, the average of the deviations is always 0? Because the positives and the negatives cancel out. Well, these are deviations from their regression line. They really are deviations from the average within each vertical strip, so that it's the same thing. And that's why I can't just say, oh, I'm just going to give you the average error, because the positives and negatives would cancel out. So why don't I just neglect the sign and just say, oh, the typical size of the errors, neglecting sign. Why don't I just give you the average of the absolute value of the errors? Well, the only reason we don't do that is because we never do that in statistics, because algebra, that absolute value function is a very difficult function to work with algebraically. And so we never use that. So to get rid of those signs, what do you think we do? Square them. Just like we did with the standard deviation. This is a standard deviation. It's a standard deviation of all these little distances. That's exactly what it is. Or you could say, okay, you take the error, the size of the errors, you square them. You take their average, the mean, and then you take their square root. It's the definition of a standard deviation. So we're taking the standard deviation of all these errors and using them as the typical size of your error. So that's all this is. Okay? That's what this says. All right, let's turn the page. Now, does this look familiar to you? The standard deviation rule of thumb from the normal distribution. About 68% of the points lie within one standard deviation. Remember our normal curve? And between z equals -1 and z equals +1, what's the area between those two boundaries? 68%. And look at this rule, 95%. Between z equals 2 and z equals -2, we know is what? What's the area under the normal curve between those two z-scores? Between 2 and -2, come on. 95. Now, I'm not going to go into detail about why this is true, and it's not true it's not true with every scatter plot, but in general, this same rule applies. You can think of, within any little vertical strip, I don't know how to draw this, but within any little vertical strip, you can think of a normal curve whose average is centered right at the regression line, and 2/3 of the points are within 2 root mean square errors away. Let me show you some real data, and I think it will help you. So let's go to our PC, and let's go to our, okay. So this is data about, on the x-axis is how much you party per week, and the y is how much you drink per week. This is from our own survey data. And here's our stats. And boy, did your party, this is a very low partying class. Only 6.5 hours per week for the average. Usually it's about 10. I'm proud of you guys. You're studying. Look at all you low down here around zeros. 0 drinking, 0 partying. Clean living. Very good. Now, if you look at the regression line here, first off, I should show you these residuals. These are your errors. Here's your regression line. Everybody who's off the regression line has an error. Like this person, huge error. This person parties very rarely, maybe an hour a week, and yet, number, what is that, 162, is drinking quite a lot. Way, huge prediction error, almost 50. That person is drinking alone. Not at a party, in his room, maybe together with the other few. Who are they? There they are. Well, that's a party if they're together. But anyway, it's a big residual. Similarly, is there a fellow or somebody out here? It shifts around a little bit. 132 is partying all the time. All the time. Never a drink passes his lips or hers. Look at that. Sober as can be. And look at that prediction error. Huge. So another way we can look at these errors, whereas here's somebody, these people right on the line, where this regression line is predicting exactly, perfectly, from how much they party, everybody on this line has no error, none whatsoever. It's making a perfect prediction. Now, if we look at this residual plot, what I'm doing is I'm going to clean this up. Well, I don't have to clean it up, but all I did was straighten this line out at 0 so I could see how big these errors were. And if you look at the statistics, now you can see the average error right here is 0. But the smallest one is this person, negative 61.629. It's much easier to read it now. And the largest one is 48. It must be one of these two people, 48. He's drinking 48 more drinks than predicted. That's huge. But what I'm saying is if you go 1 standard deviation out, 1 root mean square error from the regression line, and then 2, first with 1, you get about 68% of the points. And then if you go 2, you get about 95% of the points. There's still some people outside, about 5% are outside or out, way far out on the tails of the distribution, but just about everybody is included within 2 standard deviations, about 95%. And that's true for most data sets. Like you can look for, let's look at ACT predicting GPA. There, it's pretty much the same thing. There's some people outside, but about 95% are within those. Okay? So let's go back to the overhead. So the typical size, that standard deviation line that I just showed you, how do you know how to get that standard deviation of all the errors? Wouldn't it be horrible to have to take all 900 of your data points, figure out their distance from the regression line, and then what would we have to do? Square them, and then take their mean, and then take their square root? It would take us forever. But luckily, we have this handy formula you'll love, because you can do this so fast. This formula computes the standard deviation of those errors. It computes the root mean square of all the errors without you having to square them. Calculate the errors, square them, take their mean, and take their root. So let's look at this. And I think you'll remember it better if you understand sort of how it works in two extreme cases. It's always useful to do two extreme cases. One extreme case is when r is 1 or negative 1. When r is 1 or negative 1, what does r equal 1 look like? All points are on a line that slopes up. What does r equal negative 1 look like? All points are on a line that slopes down. Now, you tell me, is there any error here at all? Is any point off the line? So there's no error. There's no residuals, no error. All the errors are just zeros. So you have no error. I'm just using the language so you know it. All the prediction errors or all the residuals are what? Equal to 0. There's no distance above or below the line. So the standard deviation of the errors, if you have a list of numbers that are all zeros, what's the standard deviation of that list? If every single error is 0, do they vary at all? The typical size is 0. So the standard deviation of the errors is just 0. And let's just check that our formula gives us that. What is our formula? And it's good for you to write it down so you remember it. What's the formula? Write it down. It's the root mean square error, you can write it down, or the standard deviation of the errors, I don't care which way you write it, is equal to the square root of 1 minus the correlation coefficient squared times the standard deviation of y. And y is always the variable that you are predicting. Y is the variable you are predicting, always. Okay, so if you're predicting drinks, y is drinks. If you're predicting partying, y is partying. So in this case, we want to get 0, do we? When r is 1, this is what I'm talking about. Don't lose sight of what I'm doing. When r is 1 or negative 1, what does this work out to be? Put a 1 or a negative 1 in for r and see what you get. It's 1 minus, let's see if it's plus or if it's minus. It doesn't matter. It's plus or minus 1 squared times the standard deviation of y. What's under the radical there? What is that? 1 minus 1. 0. What's the square root of 0? 0. 0 times anything is 0. So we get 0, and it checks out. Isn't 1 minus 1 0? Any questions on that? I just want to show you the formula works with your intuition. What's the other extreme case? When r equals 0. When r equals 0, what would it look like? When r equals 0, it means that no matter, this is r equals 0. It means no matter what x is, I don't care if x is down here or up here, you can't, there's no pattern. You have no knowledge of y given x. And so this is y. And so always your best bet, given x, would be to guess the average of y. All right, there's the average of y. And how far would you be off by? You'd have a lot of error. There's error, there's error, there's error, there's error, there's error, there's error. These are all your deviations from the average, would be your error. The typical size of the deviations from the average would be your error. And we have another word for that. The typical size of the deviations from the average is known as the what deviation? The standard deviation of y. So that would be your error. That would be your error. The standard deviation of y would be your error. The typical size of the errors would be the standard deviation of y. Okay, so let's make sure. So our error should be the standard deviation of y. Let's make sure the formula works out. See if the root mean square error equals the square root of 1 minus r squared times the standard deviation of y. And when r is equal to 0, we should get just this. And so it does check out. So what this is telling us is that what's the very smallest error we could have is 0, and the very biggest we could have is the standard deviation of y. So the smallest, so we can say 0 is the very smallest the root mean square of the errors can be. This is the smallest it can be. It has to be wedged between 0 and it can never be bigger than the standard deviation of y. That's the biggest it can be when you have no correlation. You're going to have an error. If your standard deviation of y was nothing, was 0, then all the points would be on the line here. Or if you have very small standard, then you'd have small error. All right, time for an iClicker question. So let's go get out your iClickers. All right, let's do the first one, number 1, and I'll start it. We're doing number 1. Choose A, B, C, or D. Okay, can I stop? Yeah? Okay, I'm stopping. Scream if you don't want me to. Okay. All right, let's see what it looks like. And 0 was the right answer, correct. Okay, 0. Because it's perfect correlation, you have no error. We're doing the next one. All your errors are 0. So now you're on this one. Okay, time to stop. Stop. All right. And let's see what you wrote. 0 again. Very good. Now, the next one. We're doing 3. And this is just like your homework too. So you can do this, there's a homework question. Let's do Wednesday on this, you'll get that, no problem. It's just exactly, pretty much like this. All right, can I stop? All right, and you should all have C. Very good. And let's do the last one. This one, number 4. And then we're going to do the next page after we do that. And then we're going to do some regression estimates using our own data from our own survey responses. And calculate the standard deviation of the errors. All right, time to stop here. Yell if you don't want me to. Okay, I'll stop. And the answer should be C. And you got it. Good. All right, now let's go to the next page. All right, so for student 1, for each student, is his residual positive, negative, or 0? Okay, so let's just, positive, negative, or 0. Let's start with student 1. Student 1's right there. Positive, negative, or 0. Remember, if it's above the line, I'm just going to tell you it's positive. If it's below the regression line, it's negative. So I think you're going to get this one. All right, so we'll stop this now. I'm just going to give you one that's a little more difficult, but I don't see it. All right, I'm going to stop this one. So this one's positive, right? Yeah. What I wanted to do was give you one that was in between. Which one's the regression? What I want you to answer, I wanted to give you one right in between, but there isn't one. Between the two lines here. How about, should we do this point right? I'm going to give you this one right here. This is the point. Can you all see this point? It's in between this line and this line. And I want you to answer this question, whether it's positive, negative, or 0. And this is the point right here. Can you all see it? Okay. Answer positive, negative, or 0 for that one. Which line are you looking at is the question. Which is the regression line? Okay, I'm going to stop this. And positive is A, and let's see if you got that. The A is right. Yahoo! Okay, I think you got this. And how about just this one, 2? Let's just do 2, this one. Is that it's right on a line, but do you think it's positive, negative, or 0? We're doing number 2. You're getting these all right. This is great. And then we have some work to do. Okay, I'm going to stop it right now. And let's see what it looks like. Positive, great. This one right here would be 0, because the regression line is the line that's less steep. All right, now let's go and look at our own data here and get rid of this. And let's look at, I wanted to look at the party and the drinking. Party hours versus drinks, number of drinks, and I don't want the residual plot, and I don't want any of this stuff here. All I want to do, and I want to clean this up, okay, and here's our regression line, and here's our SD line. Now what I want to show you is our stats on this, show the stats. And I want you to copy them down in your, I'll read them to you, but turn to page 101, and we're going to do some problems, make regression estimates with our own data here. So, for Party hours average. There's a blank there. Let's fill it in with 6.5. Party standard deviation, 6.6. Now let's move down to the drink line. We're on drinks. The average. Do you want to do 8.4? Just stick with what it says here, or 8.5? What do you want to do? You like 8.5? Okay, that's what the other class wanted. 8.5. For some reason you like those and 10.7 for the drinks. Now, all right, where's our correlation coefficient? We need that. You probably can't see it. It's way up here, and it says 0.7542, 0.75. All right. Now let's go back to the document camera and do these regression estimates. All right. Okay. So we didn't see what N was. This semester, I don't know how many, we forgot to fill that in, what N was. We can look back later. All right, but lots, about 900 students. You guys, this is your data. You have a lot fewer partying hours than last semester. Okay, predicting drinks from partying. Let's predict how many drinks per week someone who parties 20 hours a week has. Anybody in here party 20 hours a week? Okay, so this goes out to you. We'll see how close it is to your drinking behavior. All right, so we're gonna start with 20 hours right here. 20 hours, and we need a calculator. We need a calculator because these numbers, so 20, you tell me what to do. I wanna get to the z-score, so I say minus what? 20 hours minus what? 6.5 hours over what? Over what? 6.6. Let's do it. We can do it together. So we're going to say 20. Can you see this? 20 minus, can you see it? 6.5 divided by what? 6.6. Tell me if I make a mistake. That's 2.04. Why don't we round it to 2.05, but let's leave it in the calculator like that. You'll get a much more accurate, just because I don't want to write down all those decimals. So let's just leave it like this, because what's the next step we're going to do? What should I do with that number? I'm going to multiply it by what? By 0.75. So let's do that. Times 0.75, and of course you're going to get a number closer to 0. And now, here we are with the z-score for drinks. That's what we're at, and what is that? About 1.53, but leave it like this. Don't, on your calculator, just leave it like this. It's so much better. You'll get an accurate estimate. And now what do I want to do? What do I want to do here? I want to get the number of drinks. What is this? Is that the number of drinks, or is that the number of standard deviations? Standard deviations. So shouldn't I just multiply that by what? By the number of standard deviations. But what should I put in here? What am I at? I'm at drinks. I want to end up with drinks here. So what's the standard deviation for drinks? Look at it. What is it? So you multiply by 10.7, and what's this number tell you? This number tells you that 16.41 tells you that this person is 16.41 drinks above the average. Now we're at drinks. That's how many more than the average person that they're drinking. Now I'm going to add it to, so this is times 10.7, and what am I going to add it to? The average. The average for what? Drinks, because we're at drinks. And the average for drinks is 8.5. So all I have to do, you can do this all in your calculator, and I add it, and I get add to 8.5, and I get 24, can we approximate it to 25? approximately 25 drinks. You can round it at the end. 24.91, about 25 drinks. Does everybody see that? Does that make sense? Now, somebody who does party 20 hours per week, does that sound about right? I mean, that's about, think about it, it's about 1.25 drink per hour. So some people raise their hands, is that about right? Does that sound right, or does that sound too high, too low? About right. You're a 20-hour drink guy? Okay. I mean, 20 party hour, 20 party. And what's your actual number of drinks?
20.
About 25? So it's pretty good for you. How about the other people? All right, so I made a pretty good estimate. But how far off do you think this estimate is likely to be? So I would estimate 25, but I wanted to put some margin of error around this. And that depends on what? What is this question asking me? This asks me, when you give an estimate, 25 drinks, I'm not going to say right exactly on the nose. I'm going to say, I think, give or take about something or other. Put that margin of error in there. And what that is your typical error. The margin of error, also known as what? The root mean square error. And what is that? The square root of 1 minus r squared times the standard deviation of y. So, for him, I was right on the money, but for other people, I want to give myself a cushion here, because not everybody, it's not a perfect prediction. I want to say for about 68% of the people, it'll be 25 drinks plus or minus what? Now, how do I do that? I have to say the square root, I didn't leave myself enough room, so I'm going to put it over here. The square root of 1 minus, what's r squared? 0.75 squared. Let's do that so far. So I'll take this out, and I'll take, okay, the square root of 1 minus 0.75 squared, what is that? Let's see what that is. That's 0.66. It's always going to be less than 1. This is how much it's going to reduce your standard deviation. The typical range of the drinks. If you knew nothing, you'd guess the average and you have this range of the drinks. So it's 0.66 times, now which standard deviation do you think I want? I'm talking about drinks here. I'm saying 25 drinks, give or take some amount of drinks. So don't you think I want to multiply that by the standard deviation for drinking? I don't want to say give or take some amount of party hours. So I have to multiply this. So far I've done the square root of 1 minus times, you tell me what I want to put in here. Standard deviation of y. Which one's y? It's whatever you're predicting, it's drinks. So in this case, which standard deviation do we want? 10.7. And it's going to reduce that. You're going to have less error than 10.7. So you multiply it by 10.7, and I got 7.077. I'll say that's about, this is about 7. This whole thing is about 7. Do you understand? Did I make that too messy for you? Do you have it? All right. Now, suppose he really only has 20 drinks per week. Suppose he only has 20. Now what? Well, let's think about it. How far off was your prediction? The best way to think about this is, okay, we predicted, just draw it. It's right on the line. Your prediction is right on the line. So your prediction is always on the line. It's always on the regression line. And what is that point that we predicted for him? 25. But he's really not up that high. He's down here at 20. What is that distance? That is his error. That's our error in making the prediction. What is that? It's -5. And what I'll say is the prediction error is equal to the actual That's the actual minus the predicted. So it's 20 minus 25, which is -5. But if you don't get confused about which way you subtract, just know if he's below, you put a negative. It's a distance of 5. You're off by 5. If he's really under what you predicted, it's negative. If he's above the line, it's positive. Now, about 68% of the time, our predictions of drinking and partying will be right to within what? Hint. Remember the standard deviation rule of thumb. I don't expect you to remember this right off the bat, but it was this, that about 68% of the points are right to within one root mean square error. That's what we're talking about. So let's write that down. 68% of the points usually, and in this case it's true, are within, it's not always the case, but one root mean square error of the regression line. So, what is one root? What is that? Do you remember what we did? Do you remember what that number is? Look back up. I already forgot what it is. It's our margin of error here. It's 7. When we put that margin of error in there, we're saying, I bet about 2/3 of you who party 20 hours a week are going to be between 25, give or take 7. What does that mean? If I went down 7, that would be down to 18. So I bet between 18, and if I went up 7 from 25 gives me what? 32. Between 18 and 32. Is anybody outside that range who parties 20 hours a week? Sure. But if I went 95% of the time, I'll be right 95% of the right. If I really want to be sure, if I was betting money on this, 95% of the points, I'd say, are within what? What do you think? 95 goes with what on the normal curve? 2 root mean square errors. So about 95% of the time we'll be right to within 14 drinks. Do you know what I mean by that? I mean 25 plus or minus 14, which is what? The lower limit would be what? 11, and the upper limit would be what? 39. So I bet 95% of you, if you party 20 hours a week, you're drinking in that range. Whereas 68% of the time would be what? 25 plus or minus 7, which translates into what? 25 minus 7 is 18, all the way up to what? 32. Does this make sense to people? Do you understand what I'm doing here? What? The number of people, how many people filled out this survey? Let's go back and see. She wants to know. Whoa, how many people? I have to go to the statistics. 854. Actually, I think there are more. Weren't there, David, more than 854? We didn't update that. I think it's more like, maybe it is 8. Let's write 854. All right, thank you very much.